Hello, my name is Andrew Hoyle. I am a senior at Davidson College, and I would like to talk to you today about the research I did over the summer in collaboration with Jefferson Lab and Davidson College Alpha. Alpha stands for Algorithms for Learning with Physics Applications. So first is background. The purpose of this project was to build an AI environment that we could use to understand hadronic structure. My specific work was devoted towards using machine learning methods to generate structure function surfaces for physics extraction. I had two main methods for going about this. The first method was the use of a regression model, which would take in kinematic variable inputs, x, q squared, and z, and produce associated structure function value predictions. The second method is a GAN model, which stands for Generative Adversarial Network, which is a model which is composed of actually two models which compete against each other. The first model is a generator, which takes in a random input vector, and in our case, a condition S, which is a kinematic variable, which is determined by the beam energy of your specific event. And it takes those and it produces the entire structure function surface relative to those kinematic variable ranges. The discriminator takes in the generator output and it evaluates it on a scale of -1 to 1 on how realistic it thinks it is. The idea is that the discriminator output can be used to inform how the generator output can get better. For training, both of these models were trained on deep and elastic scattering event data, both inclusive and semi-inclusive. And the distinction for between semi-inclusive and inclusive, insofar as this project is concerned, is really only in the equations that we use to go between structure functions and cross-section, and also how many kinematic variables we use. For inclusive, we use x, q squared, and z as our kinematic variables. And for semi-inclusive, we use just x and q squared. We were able to train the regression model on both inclusive and semi-inclusive DIS datasets. At the top here, you see a correlation plot for our semi-inclusive test results. These plots show the correlation between our predicted surface values and our true surface values. As you can see here in both of these plots, the correlation between them has a slope of almost exactly 1, which is really good. That means that our predictions are almost exactly in line with what the true value is. These plots are continuum plots, which show the ratios between the true and predicted F1 and FL, or structure function values, relative to a specific kinematic variable. So in this case, you have x, in this case, you have z, in this case, you have q squared. These are also pretty good. They tend to center around 1. However, there are some problem regions. Specifically, this area of the x continuum plot, at low values of x, essentially, events are pretty, like, they're not nearly as likely to happen. So therefore, our event data has very few cases in this region, like where the x values are that low. So therefore, there's not nearly as many samples in that region to train on, and our model does poorly. We're still working on trying to get these regions up to the same level as the other regions of these variables. The GAN, while theoretically promising, is still very much a work in progress. We still have not completely nailed down the structure of the generator and discriminator. We are still actively experimenting with those. Within this image on the left here, you can see the comparison between the structure function surfaces, the true and the predicted. We have our F1, F2, and cross-section predictions on the left, and their true counterparts on the right. Visually, these look pretty similar. However, if we take a look at these residuals histograms, we see that there is definitely work to be done. So a residuals histogram is essentially just a histogram showing the distribution of the difference between our true and predicted surfaces. As you can see, this one for F1 is centered around about 0.02, and the one for F2 is a little bit greater than 0. Ideally, both of these should be heavily centered around 0, and the distribution should be very thin. But since these are works in progress, we're still working towards that, and we hope to have good results for you, hopefully by next DNP. I have been Andrew Hoyle. I have shown you my research. I hope to see you all at DNP, and if you have any questions about what I said here, please feel free to contact me.